Picture this, you're sitting in your Manhattan office at 9 a.m. By 10 a.m., you're having lunch in London. Not in 7 hours on a cramped airplane, in 55 minutes, shooting through a tube under the Atlantic Ocean at 1,200 kilometers per hour. This is Elon Musk's $20 billion promise, the Hyperloop. A transportation system so fast it could make every airplane on Earth obsolete overnight. The Hyperloop hits 1,200 kilometers per hour. Musk isn't just promising faster travel, he's promising to rewrite the physics of human movement. But here's the question that's been haunting engineers for a decade. Can this dream survive reality? Or is this just another Silicon Valley fantasy burning billions of dollars? August 2013. Elon Musk drops a 58-page document that breaks the internet. It's called Hyperloop Alpha. Not a product launch, not a company announcement. A white paper that reads like a blueprint for the future. The idea sounds deceptively simple. Take a tube, remove most of the air to create a near vacuum, float passenger pods on magnetic cushions, fire them through this tube at airplane speeds. The result? Ground transportation faster than flying. Musk's first proposal was modest by his standards. San Francisco to Los Angeles in 35 minutes. The same trip takes 6 hours by car, 1 hour and 20 minutes by plane when you include airport time. The Hyperloop would cost passengers just $20 per ticket. But here's what Musk didn't tell you about the real price tag. While he claimed this revolutionary system could be built for $20 billion, transportation experts who've studied the engineering challenges estimate the actual cost would be somewhere between $100 billion and $21 trillion. That's not a typo, trillion with a T. Let me paint you a picture of what this looks like. Imagine stepping into a sleek pod that looks like it belongs on a spaceship. The pod slides into a steel tube wider than a subway tunnel. You feel a gentle push as electromagnetic motors accelerate you smoothly to 300, 600, then 1,200 kilometers per hour. No turbulence, no noise, just the sensation of gliding through space. The stations would be architectural marvels. Think of Apple Store minimalism meets NASA mission control. Passengers would arrive just minutes before departure because there's no security theater, no baggage checks, no cramped terminals. You step into your pod and you're moving. But Musk did something unprecedented. Instead of keeping this technology locked behind corporate doors, he made it open source, free for anyone to build, improve, or compete with. His reasoning was brilliant. If someone can build this better and faster than me, the world wins. The response was electric. Within months, hundreds of startups registered to chase the Hyperloop dream. Universities launched research programs. Engineers who had spent careers making cars go faster suddenly saw a chance to reinvent human transportation from scratch. The numbers being thrown around were staggering. A Hyperloop network connecting major American cities could generate hundreds of billions in economic activity. Property values would explode in smaller cities, suddenly connected to major job markets. Airlines would have to completely rethink their business models. But the most intoxicating part wasn't the money. It was the engineering challenge. These weren't just startups chasing another app or social network. These were teams trying to solve problems that had never been solved before. What happened next was pure Silicon Valley magic, the kind that turns PDF files into billion-dollar industries overnight. Richard Branson, the billionaire who built Virgin Airlines, Virgin Galactic, and Virgin everything else, saw the Hyperloop white paper and made a decision that sent shockwaves through the transportation world. Virgin would build this thing. They partnered with Hyperloop One, a startup that had raised over $400 million from investors betting on Musk's vision. Suddenly, this wasn't just Elon's crazy idea. This was a legitimate business with serious money behind it. SpaceX, Musk's rocket company, announced the Hyperloop pod competition. They built a test track at their headquarters and invited engineering teams from around the world to compete. MIT, Stanford, universities from Germany, Canada, and dozens of countries sent their brightest minds to California with prototypes that looked like miniature spacecraft. The media coverage was intoxicating. CNN called it the fifth mode of transportation. The BBC compared it to the invention of the airplane. Tech journalists wrote breathless articles about the end of aviation as we know it. Investment flowed like water. Hyperloop transportation technologies raised money. Transpod in Canada secured funding. Hyperloop TT signed agreements with governments. Everyone wanted a piece of the action because everyone could see the same future. A world where geography didn't matter anymore. The numbers being thrown around were mind-bending. A Hyperloop network connecting major American cities could generate hundreds of billions in economic activity. Property values would explode in smaller cities, suddenly connected to major job markets. Airlines would have to completely rethink their business models. But the most intoxicating part wasn't the money. It was the engineering challenge. These weren't just startups chasing another app or social network. These were teams trying to solve problems that had never been solved before. How do you maintain a vacuum in a tube stretching across continents? How do you levitate a passenger pod at supersonic speeds? How do you make it safe enough that governments will approve it? The Hyperloop had become more than transportation technology. It had become a symbol of human ambition, proof that we could still build impossible things. Then physics showed up to the party. The first cracks appeared in the most fundamental assumption, the tube itself. Maintaining a near vacuum in a tube stretching from New York to London isn't like creating vacuum in a laboratory. We're talking about a tube 5,500 kilometers long, sitting on the ocean floor, dealing with temperature changes, seawater pressure, and geological shifts. Every seal, every joint, every meter of this tube would need to be perfect. A single leak could create catastrophic pressure waves traveling at the speed of sound. Imagine a passenger pod hitting that pressure wall at 1,200 kilometers per hour. The safety challenges multiplied exponentially. In an airplane, if something goes wrong, pilots have minutes to react and multiple backup systems. In a Hyperloop pod screaming through a vacuum tube, passengers would have seconds before disaster. Emergency stops at supersonic speeds are potentially lethal. Then came the passenger comfort problem. Airline passengers complain about turbulence at 35,000 feet. Now imagine experiencing G-forces in a confined pod traveling faster than most military jets, with no windows, no escape route, and no pilot. But the real wake-up call came from the business side. Hyperloop One, the company that was supposed to prove this technology worked, began burning through cash at an alarming rate. Despite raising over $400 million, they couldn't deliver on their most basic promise, a working system that could carry passengers at the promised speeds. Their first major test was supposed to be a triumph. Instead, it was a sobering reality check. Despite all the hype about 1,200 km/h speeds, no Hyperloop prototype has ever carried passengers faster than 500 km/h. Most tests barely reached a fraction of that speed. The harsh truth, after a decade of development and billions in investment, there still isn't a single commercial passenger Hyperloop system operating anywhere in the world. Not one. The media narrative began to shift. Articles that once celebrated revolutionary transportation began asking uncomfortable questions. Where were the passengers? Where were the promised speeds? Where was the revolution? Investment started drying up. Government contracts that seemed inevitable began disappearing. Cities that had signed preliminary agreements began having second thoughts about betting their transportation future on unproven technology. By 2022, the most devastating blow arrived. Virgin Hyperloop, the company that was supposed to prove Musk's vision, announced they were firing half their staff and abandoning passenger travel. They would focus on cargo instead. The dream of humans traveling at airplane speeds on the ground was officially on life support. A decade of hype, billions of dollars invested, thousands of engineers working on the problem. And the result? No working passenger system, no commercial routes, no revolution. The Hyperloop had become a case study in the gap between Silicon Valley promises and engineering reality. But here's where the story gets interesting. While American companies were struggling to build Hyperloop prototypes, other countries were already moving people at incredible speeds, using different technology. Take China's Shanghai maglev train. It's been operational since 2004, carrying passengers at 431 km/h every single day. No vacuum tubes, no revolutionary breakthroughs, just magnetic levitation technology that works, proven by millions of passenger trips. The ride is smooth, quiet, and safe. Passengers board normally, sit in comfortable seats with windows, and experience speeds that would have been unthinkable just decades ago. The 30-kilometer journey from Shanghai's airport to the city center takes 8 minutes. But China isn't stopping there. They're developing the next generation of maglev technology, targeting speeds of 600 km/h. Still not Hyperloop speeds, but fast enough to compete with short-haul flights and proven enough that governments are actually building it. Japan takes a different approach with their Chuo Shinkansen line. This magnetic levitation train will connect Tokyo and Osaka at 505 km/h when it opens in 2027. The engineering is conservative but bulletproof. They're not promising to revolutionize transportation. They're methodically building the fastest passenger rail system on Earth. Meanwhile, in the Middle East, Saudi Arabia and the UAE are investing hundreds of billions in futuristic transportation corridors. But they're not betting on unproven Hyperloop technology. They're building high-speed rail networks using tested, reliable systems that can actually move millions of people safely. This reveals the fundamental problem with the Hyperloop approach. While American entrepreneurs were chasing breakthrough physics, other countries were improving existing technology to achieve remarkable results. The global speed race isn't just about engineering anymore. It's about which approach wins, revolutionary leaps or evolutionary improvements, Silicon Valley promises or Asian execution, theoretical breakthroughs or practical solutions. And right now, the scoreboard shows a clear winner. Countries building improved versions of existing technology are moving passengers at incredible speeds today. Companies chasing revolutionary breakthroughs are still building prototypes. So is the Hyperloop dream dead? Not exactly. Despite Virgin Hyperloop's retreat from passenger service, other companies are still chasing Musk's vision. Transpod in Canada claims they're close to breakthrough speeds. Hyperloop TT continues signing agreements with governments willing to bet on the technology. Even China, the country dominating practical high-speed rail, is researching vacuum tube transportation. The physics haven't changed, but the engineering might be catching up. New materials, better vacuum systems, and advances in magnetic levitation could solve problems that seemed impossible a decade ago. But here's the real question. Does it matter? If China's next-generation maglev hits 600 kilometers per hour and Japan's trains cruise at 505 kilometers per hour, and both systems can be built with proven technology, do we need the Hyperloop's theoretical 1,200 kilometers per hour? The answer depends on what you're optimizing for. If you want to move millions of people safely and efficiently, proven technology wins. If you want to fundamentally rewrite how humans experience distance and time, you need revolutionary breakthroughs. Musk's genius wasn't just technical, it was psychological. He made the world believe that current transportation speeds weren't good enough, that we should demand better, that the impossible was just an engineering problem waiting to be solved. The global race for speed is not slowing down. China is developing 600 km/h trains. Japan is perfecting magnetic levitation. European countries are connecting their high-speed networks. The Middle East is building transportation systems that will define the next century. And somewhere in a research facility, engineers are still working on that impossible dream. Humans traveling faster than airplanes, closer to the ground, in tubes that stretch across continents. The race for speed never ends, it just gets faster. Speaking of impossible engineering, China just built something even crazier, a ship elevator that carries 3,000-ton vessels straight up a mountain. Yes, you heard that right. Ships going up mountains. Click here to see how they actually pulled this off. Trust me, you won't believe what you're about to see.